Okay, we study the laws of logarithms because that will help us when we get into the section on solving equations. So there are basically three laws of logarithms that we covered. They are the product rule, the quotient rule, and the exponent rule. And so if you want to use the product rule, quotient rule, exponent rule, you need to be sure that you can recognize whether you're going from the left to the right or the right to the left. One way is expanding and the other way is simplifying. So in this example, this is already expanded, so we want to combine them together as one logarithm. So this is the sum of logs, and therefore that's the log of the product. The product is 4 times 25. 4 times 25 is 100. The log of 100 is the exponent that we need on the base of 10 to get 100, and that is 2. Next we have base 4 logs, and this is the difference of two logs, and so we'll use the quotient rule. That's the log of the quotient. So it's the base 4 log of 192 divided by 3. And 192 divided by 3 is 64. And so we need the power of 4. That'll give us 64, and that's 3. 4 to the third power is 64. For this last one, we have a negative 1/2 log of 64. So we'll use the power rule. That's the log of 64 to the negative 1/2 power. To the negative 1/2 power. Kind of running into that other problem there. All right, the negative exponent, we'll flip the base so that we get to write a positive exponent. So that's 1 over 64 to the positive 1/2. And of course, an exponent of 1/2 means take a square root. So that's the logarithm of 1/8. Now we can use the quotient rule on that. The logarithm of 1/8 we can rewrite as the log of 1 minus the log of 8. And the log of 1 is 0 because the power you need for 10 to get 1 is 0. So we end up with minus log 8. You can enter that into a calculator if you want to figure out the value of it. Okay, this next group of problems is going the other way. The expression is already tight, compact, 1 log, and we're going to re-express it so that it's, well, more than 1 log. So this first one is using the product rule. So we'll have the base 2 log of 2 plus the base 2 log of x. But the base 2 log of 2 is 1, so this is 1 plus the base 2 log of x. This next one has a product and a power, so we'll start with the product rule. Base 2 log of a plus base 2 log of b squared. We can't simplify base 2 log of a, but base 2 log of b squared can be rewritten as 2 times base 2 log of b. And that's as much simplifying as we can do there. Okay, this last one's going to take a little bit of room, so we'll take it and put it up here. So this is going to use the power rule, the quotient rule, and the product rule. Start with the quotient rule. So this is equal to the log of the numerator, which is x cubed, y to the 4th, minus the log of the denominator, which is z to the 6th power. Now in the first expression, we use the product rule. This is the log of x to the 3rd power plus the log of y to the 4th power. And then for minus the log of z to the 6th, we can write minus 6 log z using the power rule. And so finally, using the power rule throughout, we get 3 log x plus 7 log y minus 6 log z. And that's as expanded as we can get at this point. Okay, so now we'll use laws of logarithms some more. We have this expression, which is just 3 logarithms added together. So the sum of 3 logs is a log of the product of each thing. So a single logarithm for a product of 5 x squared and x squared plus 5 to the 3rd power. Now the reason we get that is because this 2 log x is the log of x squared, and this 3 log of x squared plus 5 is the log of x squared plus 5 cubed. And then we can combine each of the arguments of the logs together into one product and just take the log of that whole product. And this is using the product rule. This last example is just a little bit more complicated because it has a minus. But we'll start by combining things. Here the first term will be the log of x to the 4th power. The next one is minus the log of x squared plus 1 to the 1/3 power. Notice I left the minus sign behind. I don't want to use a negative exponent. The last one is plus 2 times the log of x minus 1. I really wanted to put that 2 in the exponent, so I'm going to rewrite this as the log of x minus 1 squared. Okay, so the only thing you have to be careful with is to make sure that you put this one in the denominator because that's the one that has the minus sign. And so this will become the log of x to the 4th power times x minus 1 squared divided by, get a little more room here, divided by x squared plus 1 to the 1/3 power. And to make sure that we understand what we're taking the log of, we have this entire expression in a grouping symbol. So we began with an expanded expression and put all the factors and terms together so that we rewrite the expression using a single log. Now, I should probably erase some of these things here. I was practicing earlier and forgot that I had all these things up here, so we'll just erase a few of these. Make sure that we get a fresh start here. Okay, now we are looking at this problem that deals with the idea of wealth distribution. A mathematician by the name of Vilfredo Pareto observed that most of the wealth of a country is owned by a few members of the population, and this is known as Pareto's principle, and it states that the log of P is equal to the log of C minus K times the log of W. W is the wealth level, how much money a person has, and P is the number of people in the population that have that much money. And so the first thing we want to do is solve the equation for P. Well, we start with log P, that's the left-hand side, equals, now on the right-hand side we have the difference of two logs. We can rewrite that as the log of a quotient, so that can be rewritten as the log of C over W to the K power. And make sure you understand why it's W to the K power, because this is K log W, and the K becomes the exponent. Now, we use a property of logarithms. If the logarithm of P is the same as the logarithm of C over W squared, then clearly P must be the same as C over W. I said squared, but I meant to the K power. And in fact, now we have solved for P, because we know what P is. In part B, we're to assume that K is 2.1 and C is 8,000, and find out, and that W is measured in millions of dollars, and we want to use this result, part A, to find the number of people who have $2 million or more, and then how many people have $10 million or more. Well, $2 million or more is the wealth level in millions, so that means P will equal C, which is 8,000, divided by W, which is 2 for 2 million, to the power K, which K is 2.1. So you can work this out on your calculator and see what that number is. And then if you want to answer the second part, how many people have 10 million or more, instead of 2 here, you would just put 10. Okay, so the change of base formula is what tells us what to do when we have to calculate a base that is different from either base 10 or base E, because our calculator only has a base 10 and a base E key. So here's the formula that you can learn. There's a nice little pattern to it. Notice that if you have the log of any base B of a value x, you can rewrite that as the log of A, log base A of x divided by log base A of B, where A stands for any base you choose. And so we should probably choose either base 10 or base E. So for example, here we have the base 2 log of 5. The change of base formula tells us that this is the quotient of two logs. And we can change the base to anything we want. So let's say we change it to base 10. We would have the base 10 log of 5 divided by the base 10 log of 2. The 2 here corresponds to the original base, and the 5 corresponds to the 5 here. Now, it doesn't matter which base you use. You could use the base e log of 5 and divide that by the base e log of 2, and you would get the same exact value. In fact, you should try it both ways to convince yourself that it's true. For the base 3 log of 16, I would write the log of 16 divided by the log of 3, and then use your calculator to figure that out. You could also use base 10 log of 16 divided by base 10 log of 3. Either one would give you the same value. Now this one is kind of a strange problem. It says use the change of base formula to show that these are equal. That's clearly just the change of base formula. So we know that the base 3 log of x is equal to whatever base you want to use. Let's use base e log of x divided by base e log of 3, which can be written as 1 over the base 3 log of 3 times x. Now remember that this 1 over the base 3 log, the natural log of e, 1 over the natural log of e is just a number. So this is just a number times x. It's just a linear function. There's nothing really mysterious about it, and in fact, all it is a compression of the natural log. I left off the log of x here. I knew that something looked funny. Right here, oops, right here, I should have, right there, it should instead be log of x, natural log of x, not just x. Okay, so I have 1 over the log of 3 times the log of x. So I'm taking the log of x function and just compressing it. And so you can graph the function of base 3 log of x by just graphing it as a basic. So 1 over log of 3 times the natural log of x. I keep saying base 3 log of x, but I mean the natural log of x. So we have 1 over the natural log of 3 times the natural log of x, and it just kind of looks like that. I would recommend that you graph the natural log of x and 1 over the natural log of 3 times the natural log of x. Graph both of those on your graphing calculator and see how they compare, so you can understand why this 1 over the natural log of 3 does what it does to the graph of the natural log of x, and then it will make a little bit more sense that way.